Good afternoon, class. Let's talk about some torsional concepts and the flexural torsional concepts applicable on compression members, although we will be using same concepts on beams later. So when an axial loaded member becomes unstable globally, it may buckle in three ways. No? So we have three ways, three, three possibilities. So for the first buckling, uh, which is called the flexural buckling or simply the global flexural buckling. The consideration of such buckling is rather axisymmetrical. So it is uh, it is a bending on one axis only without any torsional or flexural torsional consideration. And this is more um, familiar or more common uh, on dual axis, okay, or a two-axis member such as a wide flange, uh, a standard beam section, okay, wherein the elements are placed in such a manner that the axis of symmetry is defined very well into, okay, the y and the x-axis. So the bending has no torsional uh, consideration, wherein at the maximum displacement, the effect of such deformation is only based on lateral translation, okay? So it only translates or moves laterally without any torsional effect. Very common to a two-axis member. So for a torsionally buckled member, such as this in letter B, so this is refers to letter A, so this is letter B. This is more common on sections which has more than, okay, more than two axes. Like a cruciform shape. Okay, so when you have a a section which is shaped like a cruciform, the tendency for buckling is to is more on the side of the torsional uh, behavior rather than the flexural behavior. Okay, so you can see here now that there is no longer any translation, but the fact that this shape rotated a certain angle, so the angle actually defines the degree of rotation, of pure rotation. So and rotation is actually the best description for a torsional member. Okay, so it rotates uh, without any translation. So this is a pure torsion, this is a pure flexural behavior. And the last one is a combination of the first and the second, which is called the flexural torsional backlink. Okay, so all of these are actually global backlinks. They are just described in a manner into which the displacement is actually considered. So for a flexural torsional backlink, this is more common to a single axis, one axis member. Okay, so one axis, such as a channel section. So you can see that the axis of symmetry, when you say axis, I'm referring to the axis of symmetry. Okay, so this is more than two axes of symmetry. Okay, so a channel has only one axis of symmetry with regards to x. So y is not an axis of symmetry. Okay, and the behavior is very clear to follow the combination of a translational displacement. Okay, so we have here translation, okay, defined by this distance delta, plus rotation defined by this angle theta. So both of the effect of torsion and flexure is combined, no, in this flexural torsional backlink mode. So the twisting about the longitudinal axis of the member is more common only with doubly symmetrical cross sections with slender cross-sectional elements, and the cruciform shape in particular is very much vulnerable. Okay, so it means to say that also the two axes or more, no? So this is two axes. Okay, so this is a two axis or more is very susceptible in terms of twisting, and this twisting has something to do with your torsion. Standard hot rolled shapes are not susceptible, but it may occur, no? And built-up members should always be investigated. Now, for flexural torsional backlink, there are two sub-cases wherein a one axis of symmetry and a no axis of symmetry are the ones susceptible to it. Okay, so the channels, the T's, double angle with equal length, a single angle, are examples of one axis of symmetry. And for no axis of symmetry, we have the unequal length angle. Okay, so one axis and no axis are very much susceptible to the number 3 behavior, which is the flexural torsional backlink. And the equations involved in this torsional consideration becomes more and more involved, stringent, perhaps because of its nature. Okay, so for torsional backlink, the Saint Venant torsion becomes the basis for such formula for the Euler critical backlink stress, which is this one here. Okay, if you will look at this, this is actually very similar to pi squared I over KL squared. Okay? Wherein I becomes your warping constant there. Okay? So, na-replace lang yung moment of inertia with a warping constant here. Okay, so it's EI or ECW over KZL squared. Plus the GJ then something to do with the shear modulus and the torsional constant, perhaps to 3% the pure torsional uh, properties. Okay. Okay, so this is of course divided by Ix plus Iy to make your units more precise. Okay, so this is pi EI over it's pi squared E over KZL squared. Okay, so if you introduce uh, the warping constant there, you must divide it by the moment of inertia here. Okay, so to make your consistent, your units consistent. Okay, because GJ has a unit of megapascal multiplied by, so if you're looking, this is a KSI multiplied by inch to the fourth. Okay, so it's a kip inch square. Kip inch square, so you have to multiply it by inch to the fourth or divide it by inch to the fourth to make your FE in terms of a unit of stress, which is KSI or megapascal. So that's the unit analysis there. So this is a torsion. If you want to see the derivation here, you can refer to the book of Salmon and Johnson. Okay, Salmon and Johnson reference. So for the lateral torsional buckling on one axis of symmetry, the formula is again more involved, no? Because we have here to include the translational, the lateral translation, and the torsional. Okay, so the lateral translation is actually represented by FEY. Okay, so this is now your flexural buckling, and this is your torsional buckling. So this has something to do with your lateral, and this is something to do with rotational or torsional. Okay, so this is like flexure and torsion. So FEZ will capture the formula of the pure torsion here. So if you look at this formula here, okay, so this is the pure torsion FE, and Z, what did I told you a while ago on the right-handed coordinate system. So this is your X, this is your Y, and this is your Z. So Z is the torsion. That's why you will see here torsion. The torsion now has a torsional formula there, and FEY has an Euler formula here, a buckling. Okay, so this is a flexural lateral buckling. So pi squared E over KL. It's an Euler, no? Pure Euler formula. So combining the two with an additional parameter of H, which happens to be a property connected to the shear center. Okay, so I will talk about shear center later if we have time. So this H property has something to do with XO, YO, and RO, and these XO, YO, RO are actually properties that refers to the shear center. Okay, so you just make use of all this reference formula and place it on this rather complicated equation based on the AISC equation E4-5. You can now solve problems on lateral torsional buckling behavior. And to make it worse in terms of the formula, okay, so for a zero axis of symmetry, the solution becomes a little bit indeterminate in the sense that the solution will evolve on the analysis and the simplification of a cubic equation in this form. Okay, so it cannot be solved directly in terms of an explicit formula. So this is a cubic equation wherein again the parameters Fe here is the Euler, okay, is the Euler buckling or failure load, sorry, yes, you can call it buckling, to be substituted on your lambda sub c squared equals Fy over E. Okay, Fex is the buckling, this is the lateral x direction. Fey is the lateral at the y direction. Fez is the pure torsion, or simply the torsional. Okay, XO, YO, RO are again the shear center. Okay, papasok yung XO, YO, RO kapag meron ng unsymmetrical property yung section mo eh. Kasi pag merong hindi symmetrical, torsion will actually be a major factor, and the one that gives you the value for the torsional behavior is what you call the shear center. The effect of the shear center is the one that is actually putting your section into a critical state when it comes to torsion. Okay, and this is equation E4-6. You just solve, no? You just solve this equation. This is a cubic equation, and get Fe. That's your target there. So in summary, this is what you do, no? So for a flexural buckling, this is a basic Euler. Okay, so for a flexural buckling or global, these are all global bucklings. This is just basically the Euler buckling load. Okay, this is Fe or FCR. For torsional buckling two axis, you get 4-4. The one with the torsional formula, so Saint Venant and pure torsion effect. So you can look into the derivation of this. And this is one buckling. This has something to do with lateral plus translational or torsional rather. Okay, when I say lateral, this is also the translational that I am talking about. And when we talk of the last formula here, we have two laterals, x and y kasi ito, ano? xy plus the torsional. Okay, so that's the summary of all the formula you may be needing. You may be needing only one, or you may be needing only this, or this, in combination, of course, of the properties of the section. Okay, so that's it. We're now ready to solve torsional problems, and maybe this example here is a very good example to introduce to you torsional problems. Thank you very much.